Hello and welcome back to the lecture of time series. So in this lecture we are going to cover a very important topic and that is called stationarity. Now this is a property of time series data which we need to fulfill to do many mathematical operations, for example regression. If we want to run a regression we want to make sure that the time series is stationary. Now, what do we mean by stationary? Now, before we actually deal with that, you remember that the time series data basically is generated through a process. And here I have just drawn one such process where you can see across different time t1, t2, t3, t4, you are generating data, right? And this data is creating your time series, right? So So when you have such process to produce your data, we call this process as a stochastic process. You remember that? So stochastic process is basically a process where like you have the variables that assume random values, right? And basically you have a series of random variables across times, right? So that is what stochastic process does. So what it means is that you do not know really the value of the variables in advance. So if you remember the double structure of variable that we spoke at some point, but it doesn't matter even if you don't know about double structure of variables. So it means when you use a process, when you actually generate data, so the outcome can take any value. So that is where we call it a random variable, right? Because we don't know the value in advance. So in this process you in this stochastic process you create these values of this generate these values of this variable. So now when you do that you want to make statistical inferences, right, about this stochastic process. And one such, the most important assumption, for this statistical inference and for mathematical operations like regression is that your this process has to be stationary. Now, what I mean by stationary is we mean that the mean and variance of the the observations that you get is basically constant, right? And as long as we are dealing with uh, normal distribution or multivariate normal distribution, we can just concern ourselves with these parameters like mean, variance, or covariance. Okay, so there are three conditions that we need to fulfill. Is that one, as I said, one and two, is that the mean and variance are to be constant across time, and the third condition is that the covariance between two time period depends only on the distance or gap between the two time period and not on the actual time at which the covariance is computed. And I'm just going to explain that. So basically, three conditions that you need to remember: that for a process to be stationary, it has to be constant mean, it has to have a constant variance, and the third is the covariance is only dependent upon the lag period and not on the stationary time. So let me just write it down. Um, so if I write down the mean as expectation of say whatever x period t, so it is actually constant, right? So then I will have, so you take any um, other time period, okay, expectation of say x p plus k, okay. So I would assume, so whatever time period you take, the mean is going to be constant. So in a way you can also say they are independent of t, it is not a function of t. Now the next one is variance. Similarly you can write variance of xt is equal to variance of x p plus k. All right. The third condition is the third condition has to do with the covariance thing. So in covariance, you're basically saying that um, the value of the variable is that the covariance is basically not dependent on t. So if you take covariance of say two values xt and xt plus j, so the value of the covariance is actually dependent on the j and not the t, not on the specific time when you took the covariance, right? So if you want to write it down, you can write like something like this. Say of, you take any value basically, x, say 0, x k equal to, I will have covariance x t, x t and x t plus k. All right. So you see, it really doesn't depend upon whether I am taking it x0 or xt. All it is dependent upon is the time gap basically, 0 to k or t to t plus k. All right. So that these are the three conditions that you need to remember when you are actually uh, you know trying to understand if the process is stationary or not. All right. So none of this, if you note, is basically a function of time. So now we are going to see some examples. So let us do some like graphical illustrations to understand stationarity. So this is one way to understand stationarity, and we'll talk about in next lecture other ways to see if a process is stationary or not, which are more mathematical. But the first entry point I would say is that you have some graphical intuition about if a process is stationary or not. So let's just draw some processes so that we can have some sense, if a process is stationary or not. So let us draw this. Okay. So you take say rainfall or whatever you want to take. Say rainfall. Let me use a different color. Okay. So this process, could it be stationary process? So here I have my t, and here I have say rainfall, whatever I write. So could it be stationary process? It is not, because you see the mean, the first condition was that the mean has to be constant, but here you see the mean is not really constant. Okay. On the other hand, we can draw something like this. Okay, still not what I wanted. So let me draw it again. Let me draw it again. Actually, it's not quite accurate here. Okay. Okay. So this one, you see that the mean is constant, variance is also constant. Uh, okay, and this one, if you take covariance between these 2 point, you know, any 2 point, like as long as the gap is same, you are likely to get the same covariance. So these, the diagram, the second diagram is actually representing uh, like a stationary process. We'll deal more about this stationary, non-stationary process, and we'll do more mathematics around it. But for now, just to have an introductory idea about it, this is sufficient. Now, one problem, if we don't have a series, I mean, you may ask, I mean, if we don't have a series, if we don't have a process which is stationary, what is the problem? The problem is, we will have, when you do regression, we will have something called spurious regression. Okay, uh, so you will have a y and x which are non-stationary, and you may get something, like the r square value or other f stat, t stat, whatever you use is significant, but whereas they're actually not related. And we'll talk in a separate video, we'll specifically dedicate to spurious regression. But just to get some idea about what we exactly mean by that, so let me just again draw. So in the first diagram, you have, say, this value, this process, which is non-stationary, right? Now I draw something else here. Okay, so this one is also non-stationary. All right. Now, if I want to express, say, this is the green one, the yellow one is my y, and the green one is my x. Okay. Now, if I want to express y in terms of x, So they will you will not be able to really do that because the uh, they're not stationary, and when that is the case, the the problem that happens is the spurious regression that happens because of the fact that you may have factors which are influencing y, and you may have factors which are influencing x, okay, and that is why they are not stationary. Now these factors might as well be separate factors, they might not be related, and that is why you see certain non-stationary y and certain non-stationary x. Now, when you have this kind of situation and the factors are not related, but still you may see x and y, they're not, you can actually get a very close sort of, a very strong sort of relationship between x and y given the curve we have here. So then what we will have is we have some sort of spurious regression. So we'll give more examples. We'll talk about papers that actually dealt with that. But for now, this is sufficient. Now the last point about spurious regression is that the kind of spuria the last point about stationarity is that the kind of stationarity we talked about is called weak stationarity or covariance stationarity, where we had all these three conditions that I just mentioned are fulfilled. Now there is something called strong stationarity. So in strong stationarity, what it means is that the distribution, irrespective of the time, irrespective of the the data point you take, the distributions are just like same. So you take like the rainfall from 1950 to 1960, 1955 to 1965. You take any part of the distribution and they will be identical. So that is what we call strong stationarity. So we'll talk more about this. For now, we'll end this lecture here.